Hi, I'm Charles Dillard with Amphenol Broadband Solutions. Welcome to our Fiber 201 training series. In this 5-part series, we will look at various fiber-related topics. Today's training will cover fiber test equipment. As you go through this training, the chat will be open, so if you have any questions, feel free to put those in the question section, and at the end of the training, I'll address all the questions. So, let's get started. By the end of this training, you should be able to recognize and describe function of essential fiber test tools, including light meters, optical loss test sets, visual fault locators, fiber identifiers, and lastly, fiber scopes. Your personal safety and the safety of others should always be your top priority, especially when working with fiber. Never look directly into the fiber. This can cause permanent eye damage. Do not touch bare ends of fiber, as tiny glass fibers can penetrate your skin and are difficult to remove. Consider lasers as always active. Be sure to wear company-approved safety glasses and goggles when working with fiber. Lastly, do not eat or drink when working with fiber. Use an optical scope to inspect the fiber. If the scope shows the fiber is dirty, clean the fiber. Re-inspect the fiber with the scope to confirm that everything is clean. After verifying, you can connect the fiber. A light meter measures the absolute power level of a wavelength in dBm, or decibel relative to 1 millivolt. Fiber optic power meters include inputs for attaching fiber connectors and are equipped with detectors designed to capture all light emitted from the fiber. They typically include modular adapters, enabling compatibility with different types of connectors. Light meters are calibrated at 850 nanometers, 1310 nanometers, and 1550 nanometers. Step 1. Prepare the equipment. Verify that you have necessary accessories: fiber optic launch cable, adapters for specific connectors, for example, LC connectors, SC, and FC. Make sure you have fiber end caps or dust caps to protect the fiber from dirt and dust when not in use. Inspect and clean fiber connectors. Use a fiber inspection scope to check for dust, dirt, or scratches on the fiber connectors end faces. Use proper fiber cleaning tools to clean all connectors before connecting them to power meters or a light source. Set the wavelength. Typical wavelengths are 1310 and 1550 nanometers for single-mode fibers. Use 850 nanometers or 1300 nanometers for multi-mode fibers. Set the unit of measurement. Choose the appropriate unit for measurement. Use dBm for absolute optical power measurement, and use dB for relative measurement for loss testing. Connect the fiber to the power meter. Connect the fiber under test directly to the optical power meter using the correct adapter for the connector type. For an example, LC connector, SC, or FC. Ensure the connection is secure to avoid signal loss due to misalignment. And finally, perform the test. The power meter will display the measured optical power in dBm or milliwatt. Compare the measured power to the expected levels for the fiber length or the equipment specification. The visual fault locator assists in detecting bends, defective connectors, splices, and other sources of signal loss. The signal can be either continuous or flashing at 1 Hz. For fiber runs exceeding 5 kilometers or 3 miles, an OTDR can be used to test and locate any continuity problems. From its dedicated port, the visual fault locator emits a red signal which becomes visible at the location of a fault on the fiber. The red light source will be visible through the coating at the location of any fiber breaks, defective splices, or macro bends. Use a fiber inspection scope to check for dust, dirt, or scratches on the fiber connectors end faces. Use proper fiber cleaning tools to connect them to the power meter or light source. Use the appropriate adapter to connect the fiber under test to the visual fault locator's output port. Set the visual fault locator to either continuous mode or pulse mode. Continuous mode provides a steady light. Pulse modes create flashing light, making faults easier to identify in bright environments. Connect the fiber under test to the visual fault locator. Turn on the visual fault locator to inject the red laser into the fiber. And finally, inspect the fiber. Follow the fiber path and look for red light escaping. Breaks in the cable will lead to light escaping where the fiber is severed. Sharp bends cause light to escape as severe bends or tight loops. Red lights at connectors or splices are due to poor alignment, cracks, or improper splicing. An optical loss test set measures the power levels with or without a fiber link to calculate the link's total power loss. The fiber link consists of a single fiber or a combination of fibers, splices, fusion splicers, connectors, attenuators, and other optical components. To measure the net loss, connect an appropriate optical light source to one end of the link and a power meter to the other. Ensure the meter is set to the same wavelength as the OLS. Then record the measured power. Verify that you have the necessary accessories such as a fiber optic launch cable and adapters for specific connector types. Be sure to use fiber end caps or dust cap for the fiber when it is not in use. Inspect the connectors on the OLTS, launch cable, and fiber under test using a fiber inspection scope. Clean all connectors with appropriate fiber cleaning tools, such as a lint-free wipe or alcohol or pre-moistened fiber optic cleaning sticks. Re-inspect the connectors after cleaning to ensure no dirt or debris is present. Calibrate the OLTS. Perform a reference measurement by connecting the OLTS directly to the power meter using a short reference cable. Record the baseline power reading, typically 0 dB. Disconnect the reference cable after calibration. Connect the light source. Attach the OLTS to one end of the fiber under test. Ensure the wavelength matches the fiber type, typically 850 nanometers and 1310 nanometers for multi-mode, and 1310 nanometers and 1550 nanometers for single mode. Connect the power meter. Attach the power meter to the other end of the fiber. Measure the loss. Connect the fiber under test between the OLTS and the power meter. The OLTS will measure the insertion loss and display the result in decibel. An OTDR, or optical time domain reflectometer, sends short pulses of light into a fiber. The OTDR then detects and analyzes the backscattered signal. The signal strength is measured for specific intervals of time and is used to characterize events. OTDR events are identified by backscattered signals and reflections. Reflections can be caused by bad connectors, poor splices, and impurities in the fiber. The OTDR sends a pulse through the fiber and detects the return signal, generating a display known as a trace or signature based on the fiber's measurement. Prepare the equipment. Verify that you have the necessary accessories, such as a fiber optic launch cable and adapters for the specific connector. Again, remember to use fiber end caps or dust caps when the fiber is not in use. Inspect and clean the fiber connectors. Inspect the connectors on the OTDR, launch cable, and fiber under test using a fiber inspection scope. Clean all connectors with appropriate fiber cleaning tools. Re-inspect the connectors after cleaning to ensure no dirt or debris is present. Connect the OTDR port to the launch cable using the appropriate adapter. Use a launch cable to eliminate the dead zone caused by the OTDR's initial pulse. This ensures accurate measurement of the fiber's first connector and nearby events. Attach the fiber you want to test to the other end of the launch cable. Select the appropriate wavelength for your test. Typical wavelengths are 1310 to 1550 nanometers for single-mode fibers and 850 nanometers and 1300 nanometers for multi-mode fibers. Set the test range to cover the length of fiber, including the launch and tail cables. Use an auto range setting if the length is unknown. Adjust the pulse width based on the fiber length. Short pulse width for short fibers providing high resolution but less distance coverage. Long pulse width for long fibers covering greater distance but with lower resolutions. And finally, perform the test. Start the OTDR test by pressing the Start or Run button. Wait for the OTDR to complete the trace. The device will display a graph showing backscatter and reflection events along the fiber length. A fiber identifier is a fiber test tool that can identify and detect optical signals without having to disconnect the fiber. Fiber identifiers can detect directions of the transmission. Clean the fiber jacket. Ensure the fiber jacket is free of dirt, dust, and debris to facilitate accurate testing. Use a lint-free wipe and appropriate cleaning solution if necessary. Check for physical damage. Look for visual cracks, scratches, or other forms of damage on the fiber. Inspect for bends or stress. Verify that the fiber is not excessively bent or kinked, as this can negatively impact transmission. Set up the fiber identifier. Power on the device. Turn on the fiber identifier to ensure it's ready for operation. Select the proper adapter. Choose the correct adapter for the specific fiber type for single mode or multi-mode jackets. For example, 250 micron, 900 micron, or 3 millimeters. This ensures a secure fit and accurate signal detection. Clamp the fiber. Position the fiber. Insert the fiber into the testing groove of the fiber identifier. Ensure it is properly aligned. Carefully close the clamp to secure the fiber. Apply enough pressure to hold the fiber firmly, but avoid excessive force that could cause damage. Run the test. Check the indicator to confirm if the fiber is carrying a live optical signal. The device will show the direction of the signal flowing, identifying whether it's transmitting or receiving. If a test tone is present, the fiber identifier will display the frequencies, for example, at 270 Hz, 1 kHz, or 2 kHz. And finally, we will take a look at the fiber scope. A fiber scope enables you to inspect the cleanliness of your connector surface. This will verify that your optical connectors are in perfect shape and very clean. Contaminated connectors are a significant issue in fiber optics, leading to increased connector loss and high reflection. According to network operators, 15 to 50% of all network issues can be attributed to dirty connectors, causing connector failures. Verify that you have necessary accessories, including adapters for specific connectors, and then also fiber end caps or dust caps. Clean all connectors with appropriate fiber cleaning tools, such as a lint-free wipe or alcohol or pre-moistened fiber optic cleaning sticks. Re-inspect the connectors after cleaning to ensure no dirt or debris is present. Insert the fiber connector. Carefully insert the clean fiber connector into the adapter on the fiber scope. Ensure it is seated firmly to maintain a secure connection, but apply gentle pressure to avoid causing any damage to the connector or the scope. Adjust the position if required. Align the connector so that the end face is clearly visible through the scope. This may involve slight adjustment to the connector's position to achieve optimal visibility for inspection. Inspect the end face. Check for contamination. Look for dirt, dust, and oil residue that could obstruct light transmission. Identify scratches or cracks. Inspect for physical damage that may require connectors replacement. Evaluate all core conditions and confirm the fiber core is clean and intact. This concludes this training on fiber test equipment. You should now be more familiar with recognizing and describing the function of essential fiber test tools. I see some questions have come through, so I'm gonna walk over to my computer and I'll start answering these questions. So I'll be back shortly.
All right, and we are back. Have a couple of questions, so let's see if I can answer a few of these. First one, what happens if the test equipment is set to the wrong wavelength? Well, if you know anything about fiber and fiber attenuation, one of the first things that we learn is that fiber attenuates at different wavelengths. So if you're at like 1310 nanometers per kilometer, you would lose like 0.35. If it's 1550 nanometers, it may be like 0.20. So if your test equipment is set for the wrong wavelength, then it could cause false pass fails on your test equipment, depending on the type of test equipment you're using. So if you're using like an OTDR, your distance to your fault may be different as well. So, there are additional settings in your test meters that may have not been covered in this training that can, lead to, false pass fails. Another example of that is that wasn't mentioned is with your index of refraction, optical refraction, and um, and what that is that as light travels through the cable, it's a lot slower than if that same light was to pass through like an open vacuum. So again, there's a formula to figure out what the index of refraction is for uh, the different mediums that light travels through. But the reason why I bring that up is that if that is not configured correctly on your test equipment, then that can cause issues with when you're trying to figure out if there's any reflections happening, the distance to the fault. So if it's set correctly, let's say if the fault is like 2,000 feet, if that index of refraction is incorrect, then that distance may be showing at like 1980 meters. So again, you just want to make sure your wavelength, your pulse width, depending on which equipment you're using, all of that is set correctly because it can lead to what's called a false pass-fail test on your equipment. So great question. Second one, why is my OTDR trace showing a huge spike at the beginning? So if you're using an OTDR or if you've ever been around a technician that's used one, chances are you'll see where they have a launch cable connected to it. And the reason for that is that when you have your test equipment connected to the link that whatever you're trying to test or troubleshoot, is that as you send out a signal or from that source, the scattering can cause what's called a dead zone. So you're not able really to see anything within that dead zone because it's happening so close to the device. So what that launch cable will do is give you enough distance so that way you're able to see that first event, whether it's a splice or connector or whatever it is. So if you are seeing a huge spike at the beginning of an OTDR trace, then chances are you may not be using a launch cable. So I would probably check that out and learn a little bit more about the launch cable if that indeed is the issue that you might be having. So again, great question. What if my power meter shows very low power, even though the link should be good? Um, Especially, great question, by the way. If you're in an area where new fiber is going in and you definitely don't suspect anything wrong with the fiber, other reasons that could cause that low power, even though you know for sure or 90% positive that the fiber link is good. It could be dirty connectors that causes it. So always, I talked about making sure that you're cleaning the connectors every time you're doing a test, disconnecting and putting it back into whatever device it is, a patch panel or backup an ONT. You always want to make sure you're cleaning those connectors, as an industry I guess, metric, 70-80% of most trouble calls related to fibers are dirty connectors. So you want to make sure that you check for that. Also, the jumpers that you're using, if you've been using a lot of, doing a lot of troubleshooting, weeks and weeks and months, make sure that any adapters and jumpers that you're using have been, replaced, and make sure everything is good. Another thing, it reminds me of one of the other questions about the wavelength is that you always want to make sure that you have a good reference. So with these test equipment, you're able to set that reference. And the big thing about it is that you're just making sure that, hey, if I were to take this test equipment out into the field, I want to know that everything prior to it connecting to the device or equipment that's going to be tested is solid. And that's what those reference that you would set in your device is for. And so when you do it, and you'll have a known good jumper, and you'll have your light source. And then basically what that would do is kind of set like a reference level of like 0 dBm or 0 dB. And what that means is that there is no loss. This is as perfect as this device can be prior to connecting it to a circuit or link that's going to be under test. And so when you do that, and then connect it to whatever link you're testing, whether it's a fiber drop, then you know for sure, for certain that your test equipment is perfect. So if there's any faults that's showing on your test equipment, then you know it has to be the connector that's connected to the drop or whatever that you added to your meter. So although a lot of what I talked about was key to like wavelengths, but also making sure that you do a proper reference when you're prior to doing any testing. It's no different than if you've done anything on the coax side of the house and you're doing, say, sweeping a HFC network. One of the first things you want to do when you're at an optical node is get a reference. So that way, as you leave the node and then you do your testing, your sweeping for the next active down the line, then in order to get that true, peak the valley that, you're trying to get at the end of your last active, in order to do that, you want to make sure you have a solid reference, at the optical node before you start, moving down the line to all the other actives. So same way in the optical field as you're setting up your test equipment. So always make sure you have a solid reference point. Let's see. Can wet cleaning cause problems with testing? So it's one of those things where kind of led with the as far as like making sure that you're following not only your manufacturing when it comes to fiber and how you handle it, whether with cleaning and everything. You don't want to, because any oil, water can all damage connectors as far as when it comes to taking away from the light. I try to avoid wet cleaning. It's not to say that there's it won't cause a problem or will cause a problem. I stayed away from it. Just because of anything that can cause any issues on that connector. So especially if you've ever taken our Fiber 201 training, 101 training, where we talked about the mechanics of fiber, and because you're dealing with a small medium, just getting water, oil, dust can wreak havoc, on your signal from one point to the other. So I don't know if that answers your question, Peter, but I try to avoid wet cleaning with testings. And let's see if there's any other questions. And I don't see any more questions, but this isn't a all-inclusive of the different test equipment that you would use in your network. We talked about the fiber identifier, the OTDR, the VFL, and the big takeaway for this training is that understanding what piece of equipment is meant for the type of test that you want to do. So again, if you want to see if there's a break in the cable, does it make sense to use a VFL for that? Well, it depends on, is it a drop, fiber drop that you're testing, whereas, you can kind of see where the break may be if it's exposed. But if you want to do end-to-end testing, again, that would lead you to use more of the optical loss test set. So again, it's understanding what piece of equipment should be used for the type of test that you need to accomplish. And I bring that up because there's other pieces of equipment that can be leveraged, like a pond meter. So there may be like a situation to where you want to be able to test a link, but have the source still going so it's not interrupted. And that's where like a pond meter can be used for that. So where you would do is just, if you're at the ONT at the customer house or business, disconnect that end drop and plug it into a pond meter's OLT port. And then there will be a port that you can leave out of that pond meter to go back into the ONT. And then that way you can test for upstream and downstream signal on the link. So again, just an additional test equipment that you can leverage as you're operating and troubleshooting your network. So, and let me just look one more time to make sure there's no more questions before we wrap up here. And I don't see any more. So again, I want to thank everyone for joining this short training on fiber test equipment. Hopefully you got something out of this. Look forward to our next installment of our Fiber 201, which will be, I think, fiber restoration. So we'll go into like the different, fiber restoration plans and procedures that if you're a cable operators, you should be thinking about. For example, having an escalation path, making sure that your fiber trailer is outfitted with the proper materials and equipment. So again, look out for more announcement for our fiber restoration training. And with that, appreciate your time this morning. And reach out to us on LinkedIn and also YouTube. You can find Amphenol Broadband Solution, where we have a host of different training as it relates to the coax side of the house as well as fiber. So with that, I'm Charles Dillard, and thank you for your time.